I'm Jared. Um, so my work focuses on automatic reverse engineering of unknown binary network protocols. And I kind of got into this because one summer my advisor's like, "Hey, like, how would you like to work on a research project? We've got this partner. They've got some unknown binary data. They've got a PCAP, and your job this summer is to spend all summer figuring out what the format of this PCAP is. And you've never done this before, and they just want to see what you do. So at the end of the summer, they're going to come in and like ask you, what do you think it is? And you're supposed to tell them. And I was like, okay, I haven't studied this. There's no class in this. And I found it really, really exciting and really, really interesting. And I was able to actually discover some things. And that kind of gave rise to my actual research project, which, years later, we're presenting work here. So in terms of what I'm going to talk about today, I was really excited to hear about like this workshop and, but I was like, oh, I got to figure out a bunch of stuff to say for 45 minutes. And then I realized this is 45 minutes where I can complain about all the things that all the pain I experienced in doing this research, like the things that you see this paper and you don't think about what were the things I was pulling my hair out over? What are the things where I'm like, the reviewers care about X. And I'm like, but don't they see Y? Like they're fixated on X and these are the things they're asking about that they seem to think are trivial, and that these are the things that are really kind of significant, but they're just oh, okay. And a concrete example of that was, in some reviews, they were like, well, how do you know if the data is big endian or little endian? Like, that seems very concerning. Like, no one could possibly know if the data is big endian or little endian. And then in later rounds of reviews, they're just like, words never even come up. So in terms of what I'm gonna talk about today, I'm gonna give you an overview of the task in case you didn't, or just a refresher. Hopefully you saw the talk. I'm gonna tell you a little bit about BinaryInferno or tool. Then I'm gonna talk about what is good representative data to evaluate a tool like BinaryInferno on. I'm gonna go into pretty deep how we gathered our inputs to run the experiment on, and then what did we compare it against. The issues we came across, and then I'll recap some lessons learned. And at any time, please interrupt me with any of the stuff, any questions you have. So the use case for my research and the tool is an analyst has a sample of packets. They want to understand the protocol. Somebody hands it to them. Broadly speaking, there's a couple of different steps that people need to perform. First, you got to kind of put things into buckets. You're like, I got a bunch of packets. I want to put all the red ones over here and all the blue ones over here. So you got to kind of make sure you have a pure sample of some format. And that's not a trivial thing to do. And then for each of those sort of buckets, you got to figure out what is the format. And that breaks down into a couple of different states or steps. You got to find where the fields are. So you got to, segment stuff. You got to say, well, what data type is this field? Is it an integer? Is it a float? And then beyond that, what does it mean? Is this the altitude of a UAV? Is this the elevation of something? Once you've done all that, you can infer a state machine and, build an automata, and you then have this beautiful thing. You've totally understood the protocol. I just focus on this step. I focus on just understanding the format, and that's what BinaryInferno focuses on. In sort of practical terms, it's a magic tool that sits there and looks at traffic that's been going across the network, and it tries to make suggestions to a human as to what's happening there. And I think a key point of this is, as I did this research, is no human ever trusts an automated tool to do this. They're super, super skeptical. You probably trust the type system of a compiler to do the right thing. But systems like this, where it's I think this is the format of this tool, a human is just okay, that's what you say, but now I actually have to go and validate it. And I think that's actually a key part of this research, that if we don't connect it back to the human element and say, human, what do you think? Like, did I get it right or wrong? You're not ever really going to want to automate it, or you're not really going to have it solved, and we're not really going to consider it automated in any real fashion. Practically, we just take the hex up there and we magically infer the colored part, and that lets us figure out the stuff down below there. So that's basically the magic. That's the process, and that's the interface basically the user gets. They put in the data, they cat it in over like standard in, and it just cuts it up and gives you back a format. So our implementation isn't actually that huge. We use an ensemble of detectors for a couple of semantic data types: floats, length fields, timestamps, and field boundaries. Oh man. I will tell you, every single time I seem to give a talk, my first instinct, like when there's a microphone, is to step away from the microphone and start talking. And no kidding, 3 times I've done that. And like the most recent 2 times, my advisor's sitting there watching me and she's like, go back to the microphone. I'm just like, how is it that I haven't learned this? So we only have sort of four things in our ensemble and 3 data types. So it's really small. And we're like, well, how do we demonstrate that this is useful in some way? How do you choose to evaluate it? What do you compare it against, and what do you run it on? We chose, there's lots of ways you can choose to evaluate, like protocol reverse engineering. You can be like, did you get it exactly right? Well, what does exactly right mean? Does that mean, it's a binary function where either you get every single fact exactly right, and if you don't, you fail? Or is it like you got the fields right, and if you didn't get all the fields right, you fail? Or is it you got to get the fields and the type right, you fail? What happens when you have multiple messages? And what happens when your protocol complexities are different? Because it's not like every protocol only has 4 fields in it. Some protocols may have 3 fields, some protocols may have 20 fields, and some protocols may have varying numbers of fields across different messages. So that's actually a kind of something you think about. You want to basically show that this tool is going to be useful when you don't know anything, but you don't know the assumptions on, or sort of the situations in which it's going to be run. You don't even know how much data the analyst is actually going to have. If they are like, I got 3 messages, tough. You got to make do with 3 messages versus, oh, I've got 20,000 messages. And some of the other work we've looked at, they're doing evaluations where they have hundreds of thousands of messages. I'm like, wow, that's great if you have 100,000 messages. In terms of how did we decide to measure the performance, we, the analysts, or we, the researchers, have to make a decision. We just chose the idea of breaking up the field into boundaries. So we have a ground truth where the fields should be broken, and then we run a tool and the tool figures out where should those boundaries go. Getting the ground truth is not trivial. You would think I can just go look it up somewhere. I can just go find out factually where these field boundaries are. That is not, that you should, the takeaway from here is, caveat emptor, beware. And so we go and we do our evaluation. And just to give you a sense of sort of what kind of results these tools are producing when they're trying to identify field boundaries, here we have, I can't see and point because I really want to get in front of that mic or in front of the screen. In the top left, we have the ground truth, and then all the other things are different implementations and the different sort of segmentations they produce, with the thick black lines being a true field boundary, the thick red lines being a false positive, or something thought there was a field boundary, and places where there's, different colored bytes that are adjacent and there's no boundary between them, something got missed. So you have a lot of different stuff, and somehow we have to distill that down into something to say to the the audience about the performance of these tools.
So do these represent different tools?
Yes.
Oh, BinaryInferno plus BinaryInferno.
Pick that one up.
So this is the ground truth for just an example data set.
This is a ground truth. We found the ground truth, and we had to decide, like, how do we actually want to serialize it? And one of the issues we ran into is you'd have these variable length payloads. Well, do you just treat it all as a payload? Well, if there's like a type field or a length field and then a length value pattern where like you have a length and then some value bytes, should I treat this as two fields? Like what's the right thing to do? Should I just say, oh, if you just guess maybe like this high level description, that's accurate? And then, so you have all these different tools you're comparing against, and there's no agreed upon standard for like what's valid. Like I understand in fuzzers, like the thing you do is you crash something, like you make the system explode, and that's sort of the metric of I give it some input and it explodes, and that's sort of an agreed upon standard of like you did the thing you're supposed to do. All these different tools sort of have different results coming out of them, and you have to map that back onto some task, and that was something that proved actually quite challenging. So we ultimately chose to evaluate our approach on 10 different protocols across a wide variety of different contexts, and we compared it against five other tools. The backstory here is, well, why did you choose these 10 protocols? And then why did you choose those 5 tools? A big part of that was, it kind of comes down to several things. What do the reviewers ask for? Because when you send it in, everyone apparently has their favorite. They heard about some paper, like I heard about this protocol reverse engineering. What about X, tool X? And most common after that is, well, what about this protocol? Like everyone has a favorite protocol, or if, they're like, well, why didn't you evaluate it on, the 3 protocols I care about that I'm really interested in? And
like automotive CAN bus.
I don't think anyone asked that, but like, I wouldn't be surprised. But yes, like exactly. It's like, why didn't we do it on automotive CAN bus? And the reason we didn't do it on automotive CAN bus is because, broadly speaking, the fields has some weird small fields. Like all the messages are about 8 bytes. Your messages are about 8 bytes long. I'll probably like say something horrible and offend the CAN bus community of, and you want to show the effectiveness of the tool for an unknown protocol, like a situation where you don't know anything and you have to you're like, I have to approximate it with known protocols. You had a question?
Part of from our discussion, but not this all either. They're honestly, it is that. Yeah, okay. So one quick breakdown as someone who grew up with open system for interconnection. There are protocols who are nested, and there are application level protocols. So I will hold that question, and I don't know if the reviewers asked you.
That's absolutely. Go ahead. That's a good question. Like you have to choose what you actually want to how
abstraction.
Like protocols are like onions, and you want to choose like how deep you want to go. I will say one of the decisions we made was most of the protocols people care about for reverse engineering, they're already being transported in something else. So reverse engineering TCP isn't really that interesting. Like it's probably going to be something that's just encapsulated in that. And so just pick some place.
Of course, but we had talks also through companion. True, but we had talks on software-defined networking and other types of flow networks. So those are different game.
I will.
We'll talk.
I'll continue on, and I think I'll get to the why did we choose these protocols? Because the why is really the why really comes down to this question of like, you don't have access to all the data you want. Like, it's not really what do you want to evaluate it on, as much as like the reviewer would say, or maybe the place you think you would use the tool. Like, the critical constraint in evaluating a tool like this is what data can you get? Like, I might want to evaluate it on those tools, like, or at these different application levels, but in fact, getting the samples is the hardest part of this. And it's hard because almost every piece of network data that's going across the wire is sensitive in some way. And nobody wants to just hand it over to an analyst and be like, oh, like, this shows what websites I have. Like, there's the Mirai botnet, and it is like, it's been out for like 15 years. So like, you know, it's not surprising to anybody. But if you want to go get like a PCAP of like, you know, command and control traffic for a Mirai botnet, nobody will give it to you, and nobody will post it because it shows systems that were hacked, systems that were being targeted. And you're like, well, that's the use case for this thing, is I want to like look at malware going back and forth, and you can't get the data. And suddenly you're like even if I can get the data, maybe I can find a couple of example packets. How do I do an evaluation where I have 2 packets? Like, that was another issue sometimes we had in the reviews, was like, well, you're showing us this works for like 4 packets. What happens when you have 100 packets or 1,000 packets? And it's actually, you know, not easy to go and get like 1,000 packets of an arbitrary protocol that like are representative and that are somehow they're realistic and somehow they're sanitized that you can actually get them. The other issue we ran into is there an unambiguous format? So like, do you know exactly what the ground truth is? And for some protocols, DHCP, I'm looking at you, there's some wacky stuff. Like, you can just have an arbitrary number of zeros of padding on a DHCP packet at the end. It's not like pad to like a word boundary. It's just like at the end, there may be as many, you know, null bytes as you want. Like, it's just like, just goes on and on and on. And I guess you're just supposed to drop them, but that's kind of that's not like a really precise specification. And especially with things like malware, you got to have a write-up. Like, you got to be able to argue, you know exactly what's going on across the wire. So when you're looking at how you're going to get the data for the evaluation, you've got like, you can make it yourself, which as part of earlier work I did. I wanted to work with Mirai, and no one would give me the data, and I couldn't find the data. So I got out VMware, and I learned how to install a botnet and how to set up bots. And I had 3 botnets running on like a MacBook Air. And then I would probe them to get my data. And I was just like, this is ridiculous. Like, I'm like doing a lot of engineering to set up something to get like a 40-byte message from each attack, like, just to make sure it's like representative. It's time consuming. You got to do something to generate sufficient diversity. So like, you can't just generate the same message. Like, think of IP addresses, you know, if it's always going to be 10.0.0.1, like, that may not actually be representative of what you would encounter in the wild. You can try looking for a public packet capture, and there are a lot of those, but usually they're not meant to run experiments on. They're meant to validate either a very simple parser, or to validate like a Wireshark dissector. So they just enumerate each of the cases. There's like 1 packet of each format. And you're not going to have huge diversity of stuff. There are a few good attempts to like give you kind of a diverse data set. There's one called the Ultimate PCAP, which is like the candy sampler of network traffic. It's like a 7 meg PCAP that just has every type of packet you could possibly want in it, but it's not like you don't have a uniform distribution. So you don't have like 10,000 of each type of packets. You have them in different proportions. So the thing we started to go look for is big big packet captures that are out there. And usually the big packet captures that people want to release are from security exercises for like capture the flags or anomaly detection, where they set up like a cyber range and they're like, we've captured all this data, we have people hack, and then we put it out there. Those are great. And that's actually where a lot of the related work had pointed to in terms of in getting stuff. I'll also say, like, there isn't really a lot of persistence of some of these data sets. Like a lot of these papers are related work are evaluating on packet data sets that, like, at that moment in time are at a URL somewhere on the web. And then that URL goes away, or that infrastructure goes away, and you're just like, well, yeah, maybe I can go get that data, but like it'll vanish. And in particular, like some botnet stuff we wanted to compare against, like it's just a URL somewhere overseas that has since gone away. And, we're like, we'd love to do it. We can't get it. The biggest problem with big security PCAPs is not the one, they're big, but when it's that big and it's a security thing, you're going to see a lot of malformed data. Because what do you do when you're doing like security work? You kind of use exploits, and what do exploits usually do? They probably violate some standard to try and like cause a system to misbehave. So you're looking through data to do an evaluation, and it's likely already poisoned or corrupt in some way. The most common way to deal with the data is using like tools like T-Shark. We've already talked a little bit about Wireshark, and for people who don't know, Wireshark is sort of a command, a visual interface that lets you see all the packets going across the network. T-Shark is just a command line version of that lets you sort of do some automated stuff to like carve PCAPs together. If you're not familiar with the PCAP, that's just the term for a packet capture. It's just a binary file with a collection of packets in it. And it lets you sort of break out pieces of packets or like entire payloads in a couple of different formats. We saw that a lot of different tools use this. This is kind of like the common thing we see in a lot of evaluations is there's some leverage of T-Shark, but that brings with it some problems. And I'll talk about those in just a minute. So we were out there looking for all these files or all these packets, and we were like looking at these giant PCAPs, and it turned out we had to like start and this is just like, find some representative protocols. And it wasn't really like, these are the protocols we have decided upon to start out with. It was really, let's go see what protocols we even can get 10,000 packets for. You have a question back, sir?
Hi, Jeremy Epstein, NSF. At the risk of throwing a bomb and then leaving because I have a taxi in 12 minutes. You may have heard, especially those of you who are American, of this guy named Mike Lindell. Anyone heard of him? Is it drawing a blank? Or
No, I think I've heard of him, yeah.
He's also known as the Pillow Guy. And he got a lot of publicity back about a year ago because he had billions and billions of PCAPs that proved the election was stolen, when he had nothing of the sort. So my question is there a way to make these PCAPs so they tell a story for mere mortals who are more likely to believe a pillow salesman than a computer scientist?
Thank you for that question. I would say that is not necessarily the focus of the work here, but there is functionality in Wireshark that at least makes it more approachable in terms of telling someone what actually took place in a PCAP across a lot of different protocols. Our work really focuses on just there is some unknown section of one protocol, and we want to understand that. I think the difficult part when you have an arbitrary PCAP and making it approachable to like sort of a consumer audience that's not maybe at a high technical level is you just have to introduce a lot of the introductory terms so that people understand, like, you kind of have to educate them inside of a minute as to how the internet works, how data moves back and forth. And then I think once you do that, it's a lot easier to sort of explain the concepts and to say, like, if we saw something like in one way or another, like what it would be what it would look like in the data. And then you can hopefully say, like, we see no such thing in the data. But it is difficult. It's difficult to understand what's going on there.
Yeah, so to add to the sort of understandability of PCAP files, one presentation I saw at it was called the GRASEC workshop at NOMS last year. They demonstrated a tool where they could take a PCAP file and generate a graph representation from it. And they had a very nifty demonstration where they could show that they graphically, because if you look at something in Wireshark, it can be quite difficult to make these connections that, okay, is this packet going from this host and that, and then they could show that, oh, these nodes are communicating with, these hosts are communicating with each other, these are the type of, I want to see every time this file moves and stuff like that. So that was a good demonstration.
I would...
Great presentation, both when I saw it before and again. So you're talking about getting more real data. And one thing that, so I went to the Internet 2, they had a training on P4 switches.
Mm-hmm.
And it was done by the University of South Carolina, I believe. And one of the things that they talked about was that they had actually built like intrusion detection systems using the P4 switches and forwarding it. And as part of their research, they were given access to the headers for all of that information. And I know that headers may not be totally what you need, but is there any way that those kind of technologies might be able to help you to get more real world data to evaluate?
We actually encounter some of the same things, where as we went out there and started looking for different types of data, we kind of found what was available and what wasn't. And generally, the payload is where the unknown protocol lives, and that's usually what's redacted. So a lot of times summary information or high-level flow information will be available, but not the meat of, like, the unknown thing that we're actually interested in. And maybe to bring it back to the slide here, like, rather than saying these are the protocols we're going to evaluate on, what we instead did was, let's go get these giant sets of data, and let's build all this infrastructure, which is non-trivial, to actually take a taxonomy of the packets we can get out of them. So, like, we're talking like, a 10 gigabyte PCAP file that we then would dice into smaller chunks, and in parallel, we would extract individual samples for known packets, like here represented by like known protocol types like A, B, and C. And then we would bring them back together to, like, kind of out of like 70 gigs of data, get us all the BGP packets, get us all the DNS packets, get us all the DHCP packets. And that was something, when we set out to do this evaluation, we just assumed that, like, somewhere out there, there's some data set from prior work that we'll be able to grab and run our evaluation on. And in fact, there was an NDSS paper from 2021 that also dealt with protocol reverse engineering. And our first thought was, well, we're going to use their data set. And I think they evaluated their tool on like sample sizes of like 100 messages, 1,000 messages, and maybe 10,000 messages. They only released the 100 message data set, which was kind of like, I would have absolutely compared against prior work, but you got to make the data available, and that seems to be a consistent thing across a lot of the different tools. Sir?
Yeah, Jared, I'm just going to give you a heads up. We've got about 12 minutes left.
Okay.
And I'm hoping you've got a slide here. You're going to talk a little bit about the evaluation of the tool, and then I would be curious to learn about any unexpected, unanticipated results.
Absolutely. So we got the data out like I said, Wireshark isn't perfect for ground truth because Wireshark is designed to help you make sense of data going across the network. It's permissive, so it'll interpret stuff as being belonging to a particular format, even when it doesn't actually adhere to the spec. It'll be like, well, I was able to parse most of it as a DHCP packet, so I think it's a DHCP packet, which means the stuff coming out of it, you can't really fully trust, like it's going to give you a ground truth, or it's going to segment data to a ground truth. It's also hard to easily pick out stuff and avoid. Wireshark will let you filter data to get a data set, but it may do it across different encapsulating protocols, and you may pick up weird implementations, like it's like NetBUI, or it's wrapped in NetBUI or something from 10 years ago. So those were issues we ran into. Finding where your ground truth is to do your evaluation, there's no single point of truth. You may look at RFCs, you may look at reference textbooks, you may be looking at blogs, you may have to look at the documentation of some system, and you may be using all of these things and then examining the data to try and figure out exactly what the ground truth is. In terms of constructing the ground truth, what we found we would wind up doing is we would take a sort of a refined packet capture, we would extract some of the data, we would look at it in Wireshark, and then we would build a parser segmenter to sort of a parser by hand based on the ground truth. Like that we sort of the combination of like what we saw in the spec and like what we observed in Wireshark to identify all the sort of failure cases where something that was erroneous was getting through. And we found that like this was something that actually hampered a lot of our results, where we're running experiments and we're not getting the results we expect. And ultimately the reason we didn't get the results we expected was because some piece of malformed data snuck through. Something that wasn't like a DHCP packet somehow got included in that pipeline. So we wound up having to be quite careful with that. And that's ultimately how we started building that into our evaluation, where we would take a set of input data, we would filter it to make sure we had something that was valid for a ground truth, and then we would send that valid data set back to the various tools to see how they segmented stuff. Maybe the biggest lesson learned is don't trust anything in terms of your input data that you're going to use for your evaluation, and validate it as much as possible. In terms of the tools we compared against, we got someone saying Zoom. It was kind of hell. Like it seemed every other tool we compared against, the implementations that we were able to get were so tightly coupled with the evaluation. It was like they designed it so you could run their experiments and produce some graphs that in LaTeX, and then like that was it. There weren't really clear places where you could use it as a tool with unknown data. So like the coupling in some of the tools of the evaluation was so tight, we had to like go in there and figure out how to build a harness to inject our data. They would use a variety of different formats as input. Like you think it's a PCAP as input, that's just not really usually the case. Usually it's a PCAP and then some custom written code that filters out those messages in that PCAP. And only if you were looking at that code do you have a sense of what the actual messages the algorithm or the approach was operating on was. Maybe the takeaway we have there is if it's meant to be used as a tool, like for a security purpose, have at least one use case or an example where you can just give it unknown input, where it will just take unknown input and will produce some sort of specification or like output that you can observe as a human. We found that systems that were not tightly coupled were actually better, where if there was some sort of an intermediate format where some halfway through the work it's writing it out to a log file that we as we could jump in and look at that log file or that intermediate output and transform that into some format we were interested in. We felt that was actually kind of really useful. Among the tools we compared against, they used a lot of different techniques, and it was really just if we could get the tool and we could get it running, and also if the reviewer said like we really want to see this tool, we would include it in our evaluation as much, even if it took a lot of work. And a lot of these all produced outputs in different formats. Some of them directly segment the fields. Some of them just give a high-level specification. Some of them are kind of like REPL environments, which people interact with. Okay, so experimental issues. The biggest issues we encountered when we were running our experiments, other than the fact that bad data got in and we're like, this thing, our theory is right, why isn't it producing the right output? And when we corrected it, it did the right output, and we're like, I should have been cleaner with my data. We had some parallelization parameters that we had trouble with. One part of our approach searches for serialization patterns, and knowing when that can be an unbounded search, or it can be a very time-consuming search, depending on the size of the data and the size of the hypothesis space. Knowing when to stop that, that was something we just kind of figured out by hand. Like, we wanted to demonstrate that, of course, our approach was tractable, but we would see some instances where if our search was bounded in time too quickly, we wouldn't produce an appropriate result. We didn't really have space in the paper to like talk about that in detail, but that would have been something I would have been really interested to explore. One thing we did do is we parallelized our search. That we didn't talk about the performance differences of different amounts of parallelization. We basically just got a reasonably big box with 40 cores and ran our experiment on that. In terms of the results, maybe the interesting things we saw were just some tools did really, really well in terms of identifying all the fields in a protocol, but had a lot of false positives. We saw that segmentation alignment approaches tended towards doing that, and that kind of gave us like an insight for maybe one last experiment. It was like the last experiment, like we've got all these tools, and we had this insight to run one experiment that was interesting. I'm going to skip over execution time. We decided to test our system on random data, because we're like, okay, so these things are finding boundaries in unknown protocol formats, right? And this whole time we've been working on this assumption that the idea is you have a protocol, you should reverse engineer it, and if you get it exactly right, you did good. And what we didn't think about the ideas like, well, is that really better than random? Like, in our case, our system was like designed to sort of avoid false positives. So what we did was we gave it completely random data to all these different tools. And maybe the experiment, which is just as a footnote in our evaluation that we were really interested in, it was when we gave some of these things like complete random data, 40% of the byte boundaries were being inferred as field boundaries. So think about that. Somebody gives you completely encrypted data, like smooth entropy, and your tool is like, 4 out of 10 field boundaries. It thinks that there's a juncture there, and it's telling you, the analyst, I've identified a field. Like, that kind of blew me away in terms of our evaluation. That if there was one thing I would suggest to all the other people doing research in this space, is not just demonstrate your approach works on positive examples, but demonstrate that it doesn't produce huge amounts of false positives on knowingly bogus data, because at some point it'll probably encounter that, and you don't want to like take a lot of time from an analyst looking at that stuff. Okay, so just to wrap up, did we use experimentation artifacts from the community? We used their implementations whenever we could get them. And I wrote a lot of shell scripts, and I did a lot of kind of crazy software engineering to knit 5 different tools to produce the same output and take the same input. We only attempted to replicate these tools' functionality in as much as they took the input and produced the output. That for some of these things, it was kind of beyond, the author could probably tell me if I was using it exactly right. And our use case was kind of, you're an analyst. You're not a PhD candidate focusing on protocol reverse engineering. You've been given a tool to help you figure out what's going on your network. What results does it actually produce? Getting representative data is hard. Like, that is the thing you will probably spend the most time on. It certainly took up about half of our effort on this project. The things we tried that prevented us from getting like, perfect results right off the bat. We naively assumed that the data was clean, and for parallelization, we had to figure out like what the right parameters were. I'll say two more things. So we used intermediate results we produced. We actually used a bunch of synthetic data to test individual parts of our tool. So we just sort of made up messages that had like a float and an integer, or like, 3 floats, or represented a serialization pattern. That is something we didn't include because it was synthetic data in the evaluation, but that's actually what allowed us to produce such a high quality result. And maybe the best advice I ever got as a grad student was from a computational cognitive science professor. And he sat me down and he said, well, before you do your analysis, before you go and collect data, the first thing you should do is you should simulate the data with the thing you expect to be able to detect. And when you've simulated the data with the thing you expect to detect, test your evaluation, test your tool on that simulated data, and verify that you can detect that signal. And if you can do that, then when you go get the real data, you should have much better success. And with that, that's all the slides I have, and I'm happy to take your questions.
All right, so I'll fill the next half an hour with questions. I think we're supposed to wrap up, but let me ask you really one, I think, final concluding question, which is that, the output of any good research should be then how do you transition this into a real world environment? And so have you given it to, I'm an operator that runs across weird data all the time, and I would love to take your tool and apply it to that with 2 caveats, and then I'll let you answer. One, a lot of the data that I see is split across multiple packets, and it's likely that they're doing small streaming, and I don't even know, which chunks I see that are supposed to be combined before you can analyze them. And the other obvious one is a bunch of them have been encoded in ASCII in some strange way, because whether it's base 64 or something else, right? So then you're layer upon layer problem.
So one, in terms of getting it into the hands of the analyst, that's my work for the next week. I need to clean up my repo and so I can release my code. And, because I'm a bad grad student and I wrote messy code, and I'd be embarrassed to have anyone look at it, but it's meant to be a user-facing tool. Like you just send the input in on standard in and it gives you a description. So it's designed to be that more than it's designed to be an experiment. In terms of the second question, in our experience, these things just show up inside, or at least for our evaluation and our purposes, they're just wrapped in like TCP. And Wireshark can reconstruct the stream across TCP segments or individual TCP packets, and that's where we've relied upon it. Splitting a stream into individual packets, that's a hard problem. That's something we've looked at and we would have to take as ongoing work. And the third question was
ASCII and base 64 type encodings.
We pretty much ignore ASCII because if you can look at it as like a string, if the data is, I believe you're asking what if the protocol is basically like text-based. We don't look at those because we figure a human is going to make more progress on that faster. That's my assumption, or at least we focused on the binary stuff just because that seemed more difficult for a human and there's less work in that space.
All right, we've got a 30-minute break, but I'm gonna eat in just a couple minutes here because this is really good stuff. Strongly encourage you to clean it up, package it, and make it available. Curious, what other next steps do you have? And I'll ask what may be a somewhat naive question or get groans, I don't know, but are there applications for machine learning or natural language processing algorithms here?
I will get it. We committed in the paper to release the tool. And I will say the fact that people here are like, will you release this tool is kind of an indication that this is not a solved problem. Because if they had a tool that was able to do this, they wouldn't care so much about like, give me your tool, give me your tool, give me your tool.
Can't bus. Yeah. Oh, I thought of another application. SETI. When you mentioned random data.
Could you remind your second question again? You mentioned Machine learning and natural...
next steps. What next steps, and then machine learning, natural language processing?
I think our next steps are we want to handle unions across formats. So there's we don't say this thing is complete and it shouldn't be intended to be complete. We want to handle unions, mixtures of formats. We want to automatically identify serialization patterns from the data itself. In terms of machine learning, our detector based on sort of architecture, there's a lot of places it'd be really interesting to train a detector using a machine learning technique by grabbing a bunch of fields of a certain type from extant protocols and training a neural net that just recognizes something specific, like I need to know if this is a GPS coordinate, or I need to know this is like maybe blood pressure readings coming off of some sort of medical device. I think that's a really interesting place to do it. I would say we didn't handle English or words in this, but it would be trivial to throw together a bigram model where it could just identify regions that would actually be text. And I think
pull out and dump them in.
Yeah.
Yeah. But also wondering, okay.
The only hard part about the bigram stuff is where does the text field end and the binary data begin? And I think that's maybe because it might not be an exactly crisp boundary and taking that into account.